Hello and welcome back to another session of Science 122, Introduction to Physical Science. We're going to continue today with our discussion of the view of the atom. Before we do so, let's go ahead and flash back to what we did last time. So in flashback, if you recall, we looked at classical versus modern physics. Okay, we looked at some of the early models of the atom in terms of what we thought the atom was actually like, with notables like Democritus, John Dalton, J.J. Thomson, Ernest Rutherford, each proposing a particular model for what the atom would look like. And then we looked at some strange puzzles of classical physics that basically brought up new questions as to what is really happening on a microscopic scale. Black body radiation, the emission spectra of light, as well as the photoelectric effect. We looked at how the problems were viewed. We looked at how coming up with solutions to these problems will actually allow you to get a better glimpse into the microscopic world. And we left off by asking you the following question. In the think tank question, you were asked the following. If all atoms are mostly empty space, why is it that when we sit down on a chair, the atoms of our body doesn't just slip right past the atoms of the chair, resulting in a pretty embarrassing moment for us? Okay, so that would be a very interesting consideration. So what we want to do now is go ahead and take a look at the answer. Let's see if we have a response from one of our viewers. Okay, let's take a look. Today we have a response from, Camden of Pearl City. And interestingly enough, Camden just saw a program on TV that actually talked about this particular phenomenon. Okay? And sure enough, it has to do with electromagnetic forces. The whole idea is that, if you remember what we did in electricity, when we talked about charges, that light charges tend to repel each other. So if we look at the structure that we came up with for the atom, especially in Rutherford's nuclear model, we know that for the atom, that the positive nuclear charges are going to be at the center, in the nucleus of the atom, whereas the electrons are then on the outside of the atom. So it doesn't matter what kind of atoms you have. All atoms have this similar property where the electrons are on the outside. So you can imagine now, let's say your hand coming towards the table surface, or when you sit down, your butt reaching near the chair, and so on and so forth. What's going on there? Well, let's go over to the elbow and take a look visually. So imagine over here that I have my hand coming down, and my hand comes down, for example. The hand is made up of atoms. So as I look at the atoms in my hand, they will have positive nuclear centers, but on the outside, we have the electrons on the outside. And now if we look at the tabletop that we're going to go ahead and try to press our hand against, the tabletop is also made out of atoms, well, different kinds of atoms, but atoms nonetheless. They will also have positive nuclear centers and also have negative electrons on the outside. So as you approach, as your hand approaches the table, what's happening is that the electrons will begin to interact with the electrons of the table first. And because they're at a closer distance than the proton of that table atom, this would then result in a stronger force of interaction. So what it means is that the repulsive force between the electron and electron interaction is going to overcome the attraction between the electron and proton, and so on. So because they're closer together, they experience a much greater force. Now, if you recall, the Coulomb force is an inverse square law, meaning that as the distance decreases, the force increases very dramatically as a square of that distance. So as you try to approach closer and closer, that force becomes bigger and bigger, until eventually you're so close that the force of repulsion is so big, you can no longer get any closer. And that's why things feel solid to us, because of electrical repulsion of electrons on the outside of atoms. And what we find is that ultimately, a lot of the things that happens with matter as it changes from one form to another has to do with interactions of electrons on the outside of atoms. So where the electrons are going to be very important in determining certain characteristics for matter in terms of its physical as well as chemical properties that we're going to be talking about later on. So keep that in mind. The electrons are the important things to consider when we look at transformation of matter and so on and so forth. All right, so with that, let's go ahead and take a look at today's objectives. So today we're going to go ahead and continue our discussion. We're going to go ahead and talk a little bit more about the dual nature of light. And we then look at something called Bohr's model of the atom. So this is now a new and revised version, that will help to explain some of these strange phenomena. And then we're going to look at something called matter waves and wave mechanics, And that would then lead us into something called quantum mechanical model for the atom itself. So with this, let's go ahead and take a look at the dual nature of light again. So if you recall, Einstein came up with the idea that light can actually behave like packets of energy in explaining the photoelectric effect. So if we go to the PowerPoint, we can see the following. So in terms of the dual nature of light, what it means is that it means that light not only can behave like waves, but it can also behave like particles. And funny thing about this is that this is not the first time that this idea has come up. Okay, so the idea was that back in the day of Newton, for example, Newton was actually one of the first to kind of propose that perhaps light can behave like particles. Okay, but unfortunately during that time, the overwhelming evidence pointed to the fact that light actually behaved more like waves, and so the idea of the corpuscular theory of light was kind of put aside. And it was not until Einstein and Planck that we revised this particular view of light. And now we know that light actually can behave both ways. So really the question then is, what is light? Is it a particle or is it a wave? So it turns out it is neither. And it can also be both. So it's kind of interesting in that sense. It's kind of like a coin, for example, like a quarter, where you have the bust of Washington on one side and the ego on the other side. If you spin the coin and flip it in the air as it tumbles, you can't really see which side is which. It is when you land and you slap your hand on it and you stop it that you begin to see one side or the other. And in the same way, when you look at light, it really depends on the experiment that you set up in detecting a particular property that you see either the light behavior as a wave or the particle behavior. And so if you set up an experiment like photoelectric effect, for example, you would then see the particle behavior of light. If you look at the interference of light, for example, then you will see the wave nature of light. And so that's the idea behind it. So nature has this duality where something can actually have two characteristics simultaneously, and being detected in different kinds of situations. So keep that in mind. Now, as strange as this may seem, what it does, it correctly explains the blackbody radiation curve as to why blackbody radiates in certain ways. It also correctly predicts the emission spectra of light, for example. It now allows us to explain why certain types of material emit certain kinds of spectra. And finally, it also explains the photoelectric effect very, very well. So all of this all points toward this duality in nature, that light has this duality. And so how do we incorporate this now into our understanding of the atom? Well, this is now going to take us now to our first topic of discussion. So let's go into it and go to our first topic of discussion. And this first topic is now the Bohr atom, the Bohr model of the atom. And Niels Bohr was actually a very young scientist at the time, and so this happened around the early 1900s, like about 1912. A very young Danish physicist by the name of Niels Bohr visited Rutherford's lab after hearing of his famous experiment with the gold foil, and he became very interested in Rutherford's solar system model, the nuclear model of the atom. And the question that he had was, he had several questions for Rutherford. And one of the questions was, what determined the size of the electron orbit? Now remember, Rutherford just said that, well, we have this nucleus there, and you have electrons kind of spinning around it like planets orbiting the sun. The problem was he did not specify as to where the electrons can be. According to him, I guess it could be anywhere. You could have some electrons that are very close or some very far. Bohr was a little bit more interested in being very specific. Well, how do you know? How do you actually assign a particular location to an electron as it orbits around the nucleus? So just like, for example, in our solar system, our planets orbit at very specific distances from the sun. So we actually keep our particular orbit pretty well in terms of a stable orbit. So what determines the electron orbits? So that was one of the questions that he had. Also, what determines the energies of the electron orbits? Once the electron is in a particular location, what tells you how much energy that particular electron will have as it interacts with the environment and so on and so forth? So that's another very important question that he wanted to ask. And finally, he also wanted to ask, well, why did the orbiting electrons not give off electromagnetic radiation? And this was a very, very big stumbling block. The idea is that we talked about electricity was that anytime you have a charge that is accelerated, where it speeds up, slows down, or changes direction, it will give off electromagnetic radiation. It will give up energy in the process. And so if you have an electron buzzing around in a circular orbit, for example, it is accelerating. It's constantly changing its direction. So the question then is, why doesn't it give up energy? Classically, that's what we would predict. We would expect the electrons to lose energy. And so what that means is this. Imagine what happens in terms of an orbiting satellite around the Earth. If we keep the satellite at a certain distance outside of our atmosphere, it can orbit pretty stably. But if it enters our atmosphere, what happens is then it will interact with the atmospheric gases. It will then cause frictional heating. It will lose energy. Now, as it loses energy due to the frictional heating, it is going to slow down. As it slows down, its orbit will decay, and eventually, boom, it will tumble down and basically crash into the ocean and break apart and so on and so forth. Okay? So the whole idea is that, okay, why does the electron not do that? Because if it radiates, if it gives off energy, you would expect its orbit to decay and eventually, boom, slam into the, okay, positive proton and neutralize it. Okay? So in other words, we would not expect to have any kind of stable atom, okay, if, okay, classical theory is correct. So how do you resolve this? Okay, that's what Bohr is trying to do. Okay? So let's see what he did. And so in answering these questions, okay, Bohr did the following. Okay, he incorporated the quantum concept of Planck and Einstein with Rutherford's model. So he used the latest, okay, information and theories, okay, in terms of trying to answer some of these questions, coming up with a brand new model. He created a successful model to correctly explain the characteristic line spectra of hydrogen. He was so successful in incorporating these ideas, this idea of, okay, the particle-like nature of, okay, Planck and Einstein, that he was able to correctly predict exactly what energy should be given off when a hydrogen gas is, basically, okay, energized in terms of the 4 lines that we see distinctively in this line emission spectrum. Okay, so let's see, okay, what else? Okay, Bohr also started with the idea that the single hydrogen electron acted as a single planet revolving around the nucleus in a circular orbit. In other words, okay, basically he started with a very simple scenario. Okay, the simplest of all possible scenarios would be the case where you have a single proton, single electron as the electron orbited around. Okay, so if you can solve this problem, then perhaps you can use that as a stepping stone to understand more complex situations when you have more protons and more electrons added to the atom itself. Okay, so with this, what you found was that, okay, as such, the hydrogen electron must then obey certain rules, okay, according to Bohr. And these rules, okay, basically started off with the following. He said that the electron could only be in specific allowed orbits with particular radii. Okay. Basically what it says is that it limits, okay, quantize the location of the electron itself. You cannot have the electron being just any old place. It had to be in certain locations. Okay? There's only certain distances away from the nucleus that the electrons can be. Okay? And that's the idea of quantization that he brought from Planck and Einstein. Okay? And he defined these orbits. Okay? These orbits are now characterized by what we call whole number values. Okay? So we can say orbit number 1 or number 2, number 3, and so on and so forth. And these numbers n is called the principal quantum number. Okay? So he has now basically assigned a particular set of numbers to where the electrons can be, and those numbers will specifically identify a certain distance of an orbiting radii away from the nucleus center. Okay? Now, furthermore, okay, Bohr stated that an electron in an allowed orbit does not radiate electromagnetic energy as long as it remains in that orbit. Now, here's something that's kind of a cop-out, basically. Okay, in attempting to kind of make sure that we have a stable atom, okay, Bohr now has to concede that, okay, we must make certain conditions true. And this must be one of the true conditions, okay, that when the electron is in one of these stable orbits, it cannot radiate energy. Now, he didn't go about explaining why this had to be. He just said that it must be so. Otherwise, everything falls apart, doesn't work. Okay? So sometimes, as it turns out, okay, we can't answer all the questions, but what you do is you do your best, okay, in basically explaining what you can see as much as possible. So even like, in mechanics, for example, we talked about the idea of inertia, okay, for an object. Okay? When an object has mass, it has inertia, it has this tendency to resist changes in motion. We know what it is. We can describe it. We look at the consequences of inertia. But if you were to ask any physicist in the world as to why masses have this inertia, have this tendency, they wouldn't be able to tell you. Okay? So there's a limit as to how much we can explain. And in this case, okay, Bohr basically kind of got into a dead end in this case, and he said, well, let's assume, okay, at this point. Okay? Later on, as it turns out, okay, we can actually explain it. But for now, okay, he's assuming this. Okay? And furthermore, okay, an electron can radiate or absorb electromagnetic energy only when it makes a quantum leap or transition from one allowed orbit to another. So in other words, what is happening is that the electron inside the hydrogen atom, okay, can actually hopscotch to a different location. Okay? That electron that is not confined specifically to only one orbit. It can actually go to other orbits that are available to it. Okay? It's kind of like, again, okay, looking at the rungs of a ladder. Okay? As you walk in the ladder, you can actually step on different rungs. You can move up and down the ladder, okay, placing your foot in the appropriate location. So the problem, of course, is you cannot put your foot between two ladder rungs, because then if you push down, you're going to fall to a lower one. Okay? So you have energy, you can climb up the ladder, or you can come back down the ladder. In the same way, the electron can actually make these transitions from one level to the next, okay, from one orbit to the next orbit. And in doing so, okay, if you want to go up to a higher orbit, it must absorb, okay, radiant energy. If it drops from a higher level to a lower level, it must give up that radiant energy. And that's the whole idea behind, okay, the light interaction with an atom. Okay, it is the absorption and emission of these photons of energy, okay, that gives us, okay, the result that we see, the emission spectrum and the absorption spectrum and so on and so forth. Okay, so let's see how this works. So basically, if you look at the simple model that Bohr had, it looks something like this. Okay, it is a planetary model where the electron is now orbiting in a certain location, and there are these orbits that are allowed, okay, for it. And so what happens during the transition? So we can see now the following. Imagine that I have the, okay, atom over here with the nuclear center, and let's say that the electron is in the first orbit, okay, in the n=1 orbit. What it can happen, of course, is that that electron can now absorb some energy. So as a photon comes along, okay, it can then be absorbed by the electron, and in doing so, promote the electron up to a higher location. Now, the problem, of course, is that you have to make sure that the amount of energy that is provided by the photon exactly matches the energy difference between the lower orbit and the higher orbit. Because if you absorb not enough energy, you have insufficient absorption, you don't go up high enough, you're going to fall right back down to original, okay, and the photon gets released back out. If you go too high, you overshoot, you might again fall back down to your original level, okay? So once you're in that level, however, then sometimes later, okay, it can now drop back to its original position. So later on, for example, it can then drop back down from the higher level to lower, re-emitting the photon, okay? So that's the interesting thing, okay? When this photon goes in, okay, the photon that went in is a different photon than the one that actually comes out if this transition is possible. And so that's kind of interesting, because when you look at light shining through a piece of glass, for example, the light that hits the glass from the outside is different than the photons of light that comes, okay, from the other side of the glass to our eyes. Because what happens is that photons that comes to the glass will actually be absorbed by the, okay, electrons in the atoms of the glass, and will then be re-emitted, okay, in this process of being absorbed, re-emitted, absorbed, re-emitted, until a new photon comes out. But it has the same characteristic as the photon that went in, same, okay, energy and so on and so forth, same wavelength. Okay, and so that's the idea behind Bohr's, okay, transition. So this quantum leap or quantum transition is what's going on. And so we can now ask ourselves, how does this relate back now to the hydrogen atom in terms of the spectral lines for hydrogen? So let's kind of take a look at it in the following way. Graphically, if we were to kind of graph the following, let's say we graph energy, okay, along the vertical axis, and then we're going to go ahead and draw in the different, okay, orbits that are allowed. Now, notice, interestingly enough, as I go from n=1 to 2 to 3 and so forth and so on and so forth, okay, the lines actually get closer and closer. What it means is that the orbits themselves are actually getting, okay, closer and closer together. And that seems to make sense, because in terms of defining the outer reaches of an atom, there's a limit as to how far the, okay, atom actually extends. And so if you have all these infinite number of orbits as possible, okay, eventually you're going to say, well, when does the electron not belong to the atom itself? And so what happens is that as you go up, the levels or the orbits actually get closer and closer together until you get to an infinite number where now you define the outer boundary, okay, of the atom. If the electron is able to get beyond that n is to infinite level, then it would then be no longer a part of the atom. It is now ionized. It has now been taken out of there, for example. And all you're left with is the positive nuclear center. Okay? And so this is what it looks like. And so as the electrons make transition from some of these higher level to the lower level, it will then give off electrons. So imagine I already have some energy, some electrons in there. So for example, if an electron makes transitions in the following manner, if it jumps from the n=2 to 1, 3 to 1, 4 to 1, and 5 to 1, for example, the energy difference between those levels are so big that the photon that it gives up is actually pretty high in energy. It is in the ultraviolet range. We don't see these transitions, okay? So it is not, okay, in the range where our eyes are sensitive, so we don't see this. So this is happening inside the hydrogen atom. As I energize it, they are giving off, okay, as the electrons jump back and forth between these different levels, they are giving off ultraviolet radiation. We just don't see it, okay? What do we see? Well, we see what happens when it makes intermediate stops, for example. It doesn't have to come from a higher level all the way down to the original n=1 orbit. It can actually go to the n=2 orbit, for example. Let's see what happens in that situation. So the electron is initially in the third orbit, and it drops to the second, we see that. Or if it goes from 4 to 2, 5 to 2, and 6 to 2, and so on. And what happens now, the energy levels are just right where the photon being given off now is in the visible range. And what we see is we see a red photon, a blue photon, and 2 violet photons being given off. And we can actually see that in the actual spectrum. So the idea in this case is that it is due to the transition of an electron between these higher orbits that we see the 4 lines for the hydrogen emission. Now the question is, in this case is, well, there's only one electron in hydrogen, so how can they make all 4 of these lines? Well, that's because in a gas of hydrogen, there are going to be billions of hydrogen atoms. So in some of these atoms, the electron is making the transition from 3 to 2 and giving off the red light. In other atoms, it's making the transition from 4 to 2, giving off the blue light, and so on and so forth. So when you add it all together, that's what we see. We see those 4 lines as a result of billions of transitions being taken simultaneously in all of these atoms in there. Now, what about other transitions? If I go now to n is equal to 3 from the higher levels, what happens now, the energy levels are so close together, the amount of energy change is so small now, you're now looking at photons in the infrared range. So in infrared range, we again cannot detect that. It is outside of our sensitivity. So while all of these transitions are possible, we can only detect visually 4 transitions. 4 transitions. The one that gives us the red, the blue, and the 2 violet lines in the hydrogen emission spectra. And this is why this is characteristic, because in all the hydrogen atoms, it has identical orbits for the electron. Those are all the same. And so as they make the transition, we only see these 4 different colors. And this was a fantastic model that Bohr came up with. Mathematically, he was able to predict exactly where these transitions should occur and how big those energy changes are, and therefore predict the wavelength of the 4 different lines. This was a perfect success for Bohr. So let's kind of take a look at the results for that. The problem was, while this was fantastic in that Bohr's model was able to prove successful in the case of hydrogen, it did not predict the spectra of any atom larger than hydrogen. So when you try to apply the same mathematical formulation to helium, for example, where you now add a second electron in there and do the calculation, it didn't work. It didn't match up at all. And so while this was a great beginning, it is still kind of lacking. It doesn't give us the whole picture. So what else do we have to do now in order for us to understand what's happening in the higher, more interesting type of atoms other than the hydrogen atom? What happens when we have multiple electrons orbiting the nucleus in an atom? Well, in this case, we need to come up with a brand new idea as to what's going on. And one of the key was to explaining why, in the Bohr atom, the electrons do not lose energy when they stay in that allowable orbit. And it took a Frenchman to come up with this particular idea and answer this particular question. So let's take a look. So basically, in around 1923, a French physicist by the name of Louis de Broglie, basically what he did was he applied the wave-particle duality of light to matter. And so his argument is that, well, if nature has this duality, if a wave-like structure can have particle-like behavior, can it go the other way around? If I start off with a particle, can a particle exhibit wave-like properties? So what he's asking is something very interesting. It's something that most people don't even think about. He's asking, like, for example, if I had a baseball in my hand, would that baseball have a wave-like behavior? See, for us, on a macroscopic scale, every time in a daily situation, when we throw that baseball, we see the baseball as a particle. We can use Newtonian physics to predict exactly where it's going to go. Once we throw it, once we know its initial position, once we know its initial velocity, we can predict what should happen to that baseball. The question then is, does that baseball have a wave-like association with it? Does it actually have a wavelength that's associated with it? And the answer, as it turns out, is yes. As it turns out, matter can also have a wave-like behavior. And this completes the duality in this matter-wave behavior in nature. And so basically what it means is that an electron must have an associated wavelength that would allow it to fit into a particular orbit. So what does this mean? Well, let's take in terms of an example. So let's talk about the wave behavior of a baseball, for example. Why is it that we won't see the wave behavior of a baseball? Well, part of it is because the wavelength that's associated with a baseball is so darn small that we don't notice it on a daily level. So for example, if you take a baseball that's being pitched by a major league pitcher at a speed of about 90 miles per hour, for example. Now, as it turns out, there's a very simple relationship mathematically that you can use to calculate the wavelength that is associated with this particular baseball. We call that a matter wave. And if you do the calculation very quickly, we're not going to worry about doing it here, what you'll find is that the wavelength associated with a baseball is going to be on the order of about 10 to the minus 34 meters. Now remember, the size of the atom is about 10 to the minus 10 meters. So this is much, 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 much smaller than an atom by several orders of magnitude. So the idea is that the wavelength associated with the baseball is so darn small that you don't even notice it. So the wiggle is so tight, we can't see it. We just see it almost as a straight line. So as the ball moves through the air, you can't see the wiggles because the wavelengths are so small. So that means in reality, if you imagine a game of baseball, okay, if I were to pitch the baseball every time the exact same way, if the ball leaves my hand from the same position, it leaves at the exact same speed, what will happen is that the ball will always pass over the home plate at the same location. There's no unpredictability in that sense. Everything is predictable, okay? So in a real-life game of baseball, the trick, of course, is to confuse the batter. Okay? If I were to play a game where I will always pitch the ball always the same, it would be no fun because the ball will always pass the plate at the same place, and it will be very easy to determine exactly where it is. But not so when you do something like this with an electron. Imagine now you play a game of baseball with electrons. Okay, how would that different than playing a game with a baseball? Well, if you use an electron, for example, if you take an electron and accelerate it using a 100-volt voltage source, you can then get it to go up to a speed that's pretty high. So the speed would be on the order of about 6 times 10 to the 6 meters per second, about 6 million meters per second. Pretty fast. If you use that now to calculate the wavelength, you find that the wavelength of the base of the electron in this case would be about 10 to the minus 10 meters, okay, roughly 0.12 nanometer. So it's about the size of what? Of an atom, okay? So that means the electron being much smaller than the electron is about 10 to the minus 18 meters, okay? It now is spread out as a wave with a wavelength of about 10 to the minus 10 meters. What does that mean? That means now it is able to spread out, and there's a lot more uncertainty as to where that electron actually is as it wiggles through space, so to speak. What it does, it gives us a whole lot of uncertainty. That means that if you were to imagine pitching an electron at your batter, okay, and the batter has to hit this electron, even though you may pitch that electron exactly the same way every time, so the electron will leave your hand at the exact same speed, in the exact same position. By the time the electron reaches the plate, it will be in a totally unpredictable position. So there will be no predictability as to where the electron is going to end up. So although it starts off the same way, every time, okay, when it travels through space, something different can happen. And that's the whole idea behind this, okay, wave-like behavior of particles. There is that, okay, idea of unpredictability in this case. So what does that mean? Well, in the case of using this concept now to understand Bohr's atom, we can now see the following. This gives us an answer as to why an electron is going to be stable in a particular orbit according to, okay, Bohr. So let's imagine that I have an n equal to 4, okay, orbit. What it means is that as the wave of the electron wiggle around, it now catches up to itself in such a way that it will constructively interfere with itself and basically become a stable standing wave. Okay? So the whole idea is that that circumference, okay, for a particular orbit is the right distance for the wave to wiggle around in such a way that the wavelength matches, okay, head to toe, so to speak, and it will be able to, okay, reinforce itself. And as it reinforces itself, it doesn't give up energy. Okay? It is a stable standing wave, okay, in terms of the wave phenomena. So if I go to n is equal to 5 now, for example, okay, for a larger, okay, radius, again, I provide a larger space, but now I can have, okay, the wave again catching up to itself. You have an extra wiggle in there, but it catches up to itself, it reinforces itself again. But what happened to the forbidden regions, so to speak, okay, the regions where you don't have an allowable orbit? Well, let's see what happens in that case. Let's say we have n is equal to, let's say, 4 1/3, for example. So in this case, you don't get quite the n is equal to an integer. So now what happens? Notice the wave now overlaps each other. And if you continue the wave, they overlap in such a way they begin to destructively interfere. Okay? And eventually the energy will cancel itself out and you lose all the energy. No stable electron configuration. Okay? So it cannot exist in that particular orbit. So all of a sudden, okay, de Broglie was able to answer a question that, okay, Niels Bohr was not able to, okay, understanding why the electron is stable in a particular orbit. Okay? And so with this idea now, you have to come up with some brand new understanding as to what's going on inside of the atom. And the key to the understanding is the fact that electrons behave like waves. They behave like waves. Okay? And so in this case, what has happened now is you have now kind of fueled a brand new movement. And this movement is now called wave mechanics. And in understanding wave mechanics, okay, this is now approximately 1925 now, okay, basically spearheaded by an Austrian physicist by the name of Erwin Schrödinger. A handful of physicists then applied this wave nature of the electron to the development of a brand new model of the, okay, atom itself. And in this case, okay, this will now bring us to the next topic of discussion, which is going to be the quantum mechanical model. Okay? So in this second one, okay, this is now the quantum mechanical model of the atom, part 1. So in this case, we now have a brand new way of looking at how the atom actually is put together. So it all starts off with the following. Okay? Basically, okay, this new theory is now known as wave mechanics or quantum mechanics. And in this case, we start off with the following. The electron in this particular model are now treated as a three-dimensional system of waves governed by something called Schrodinger's equation. It is a very high-power mathematical formulation that will allow you to basically determine where the electron is going to be. The problem, of course, is that you cannot locate the electron exactly because of its wave-like nature. And so basically, rather than electrons residing in simple orbits, this model now describes a series of probability space. And we call these orbitals where the electrons are most likely to be found. So the interesting thing about waves is that if you try to compress it into a very small space, it actually spreads out. It's kind of like what happens with ocean waves, for example. If you have a nice barrier that helps to reduce the amount of wave that comes through to a nice pool where you can have wading and so on and a nice safe swimming. If you have a very narrow opening, as the wave squeezes through the narrow opening, it actually spreads back out again. That's one of the wave characteristics, this diffraction idea, that it actually bends and begins to spread out. So if you try to compress the electron into a very localized region, it actually spreads out in space. So there's this wave behavior that's totally unexpected. So a lot of time you cannot ask where is the exact location of the electron. Most of the times it turns out the electron is going to be spread out in space. It is only when we actually detect it, when we hit it with something, that we can localize it. But once we localize it, we then have no longer any knowledge about what's going to go on afterwards. Once we hit it, after that, we don't know where it's going to go afterwards. Whereas with a billiard ball, it's pretty easy. Once you collide, hit a billiard ball with something, you can actually predict where the billiard ball is going to go thereafter, knowing the direction and the force and all that stuff that is involved mechanically. Not so with the electron. So how do we kind of reconcile this? How do we now view something that has no predictability? Well, although we don't know the exact location at a particular given time, what we can do is look at what happens over a long period of time. And so one interesting analogy that we can use is to imagine having a firefly in a very dark room. So let's imagine the following analogy. In this case, imagine having a firefly in a dark room, and here's my dark room. In the middle of the dark room, I have a table, and on the table is a jar of firefly pheromones. Now, these are the chemical sexual attractants that the fireflies will have during mating season to find mates and therefore be able to reproduce. So the whole idea is that fireflies will be attracted to this particular scent. So here I have a bottle in the middle of it. And I'm going to release a firefly in there and see what happens. The problem is, in the dark room, it is totally dark. There's no light source whatsoever. So I cannot see the firefly as it flies around. The only way I can detect the firefly is when it flashes. And so that's when I can see them. So imagine now me setting up a camera and recording every time the firefly flashes. I'll take a picture of it so I know where it is at the time of that flash. And then of course sometime later I would have no idea where it is until it flashes again. Now also notice in the dark room there's a window. So the firefly actually can be inside and outside the window at different times. So this is what it might look like. So let's go ahead and simulate the firefly in here. So there it goes, buzzing around. Every time it flashes, I know where it is. But if you were to ask me where it's going to flash next, I have no idea. And so what you find is that there is this unpredictability. Sometimes you even see the firefly outside the room, and that's perfectly okay. That's perfectly okay. So the question is, what I'm going to do with this information? Well, imagine now all this goes on, and I've taken thousands upon thousands of pictures every time the firefly flashes. Then if I were to kind of look at that overlay of all those pictures, I can see a very interesting pattern. And it might look something like this. So imagine I want to find the location of the firefly over time. It might now look something like this, where you can see each of these little dots represent the presence of the firefly in a particular location at a given time. But notice that there's a really big cluster right here in the middle where it is very, very dark. Well, guess what? That's where the firefly made most of its visits. And the reason for that? Well, that's because it's attracted to the pheromone bottle. In the same way, you can imagine an electron buzzing around a nucleus. The nucleus being positive will attract the negative electron. So as it turns out, as the electron buzzes around, although it may not have a very predictable path, it will appear in different locations, but the most likely location will be very close to the attraction that it feels, right near the nuclear center. So that's what it looks like. So now if you ask me, well, where is the firefly going to flash next? Well, I won't be able to tell you precisely, but what I can do is I can give you a probability now. I can say, well, what if I were to kind of draw a circle around all these dots, such that if I had 1,000 dots, for example, I draw a circle around the 900 that is closest to the, the bottle of pheromone. Then I can say, well, there's going to be a 90% chance that the next time the firefly flash, it's going to be somewhere inside that circle. So rather than giving you exact predictability, I will now give you a probability as to where the firefly is going to be found. And in the same way, we can talk about the probability of finding an electron around a nuclear center. So we can apply the same idea to now the hydrogen. So it might look something like this. So for example, if we look at something called the orbital, or the probability map describing the hydrogen electron, what I will do is I will draw a circle. Well, in this case, in 3 dimensions, it's going to be a sphere around the nuclear center. And what I will find is that inside the sphere, if I draw this properly, there is now going to be a 90% probability of finding the electron there. So although I don't have the exact precise location of the electron, I've got a pretty good idea as to where it can be found. It's going to be found within this region of space. And that region of space where the electron has a 90% chance of being found is now what we call an orbital. It is that region of space or probability location that we can find the electron. And this is the whole premise behind the quantum mechanical model. What we're doing is we're looking at mapping out the space around the nucleus of an atom in terms of where we can start putting electrons, where we'll be most likely to find certain electrons associated with that particular atom. So this is what it looks like. So if you kind of compare what we have done before to now, we see the following comparisons. So in Schrödinger's model, we're now looking at an electron cloud model. Rather than having very specific orbits, you're now having this fuzzy region of space around the nucleus where there is a chance of finding the electron with 90% probability. And when we compare Bohr's model with this model, we see the following comparisons. So for Bohr, the electrons were confined to circular orbits where the location is certain. For the quantum mechanical model, the electron is a wave now. It is spread out in space. So we have no location specifics. The location is uncertain. For Bohr, he was interested in the distance the orbits are located from the nucleus. In this case, we're now interested in the energy of the modes of standing waves for the electrons, where the electron can actually basically reaffirm itself, and basically constructively interfere and form a stable standing wave in 3 dimensions. And so that's the whole idea, that's the whole premise. So the question is, how do we put this together? How do we create a model that will allow us to describe where we can find these electrons for any given atom? So that will now bring us to our next topic. Our next topic is now the second part, the quantum mechanical model, part 2. And in this case, in order for us to kind of locate the electron, we have to kind of basically build a framework within which to place the electron. And the way I like to think about it in terms of a model is to think in terms of a condominium. Well, what is a condominium? Well, a condominium is a place where people can live. And so the way you do it is you build this condominium in such a way that you can then eventually basically populate the condominium with people. And of course, there's going to be certain structures associated with the condominium. In the same way, we can associate certain structures for the atom itself. Now, if I were to look at a particular resident of a condominium, how do I locate that person? Well, we need to locate that person by asking, well, first of all, on what floor is that person going to be living in? And what unit is the unit that he's living in? And also in the unit, there might be a room as assigned to this person. So once I know all that information, I can know where to go to find this person. In the same way, we can use the similar kind of compartmentalization for an atom to figure out where a particular electron is going to be located. So let's see how this works. So in the quantum mechanical model, basically we need to do the following. The first thing is that we need to look at what we call the energy states of an electron. In this case, the electron wave. What is it going to be described with? It's going to be described by 4 quantum numbers. These 4 quantum numbers kind of like, when put together, kind of like an address for the electron. It tells you exactly where the electron is going to be. So let's see what these things are. What does this address compose of? The first one is called the principal quantum number. And this one is what we call the main energy levels. And they just basically describe the most probable distance from the nucleus that the electron is going to be at. And so in the case, this is kind of very similar to the orbits in Bohr's atom, how far you are from the nucleus. In the analogy to the condominium, this is kind of like setting up the floors. So in a condo, you can have different floors that you go from the ground up. Each floor goes higher and higher. You're further and further away from the ground. You are higher and higher in energy. In the same way, this is how it's going to be working. So for this particular quantum number, we're going to use numbers to describe them. N equals 1, 2, 3, and 4. And these are now, again, the principal quantum numbers that we're going to be talking about. Now, what does this look like physically? Well, we can imagine what this might be like in terms of, again, distance from a certain location. So imagine a concert, for example. If you have to arrange for seating for a concert, what would it look like? Well, it might look something like this. So at a concert, okay, let's say I have a concert where this is now the stage where the band's going to be playing. Now you can see the rows of seats that I'm going to go ahead and arrange, okay, in front of the stage. And notice something very interesting, because when the band is playing, the sound is going to propagate in all directions. As I set up the seating, I'm not going to set up the seating exactly the same all the way across with the same number of seats. As I go further and further away, as the sound waves spread out, I can now actually wrap things around and provide more seating further away to maximize my profit to get as many people in there as possible. So the further away you are from the stage, the more seats you can put into a particular row. Okay, that seems a real ideal situation for an arena, for example, where you are going to hold this concert. In the same way, if you look at the nucleus, as you go further and further away in 3 dimensions, you have more and more space in which to put more and more electrons. The key is you can't put too many electrons into the same space because they will repel each other. They tend to be the same charge, for example. So as you go further and further out, okay, with more space to work with, you can actually spread the electron out more. You can accommodate more electrons. So that's the idea. The first quantum number, the principal quantum number, has to do with how far you are in general away from the nuclear center. And these are called the principal quantum numbers, or the main energy levels. Kind of like floors, okay, on your condo. And the second step now, then, of course, is to look at, okay, the second type of quantum number. This is called the angular momentum quantum number. Now, the name, okay, we don't have to worry about what it means, but what it does is that it allows us now to separate, okay, each main energy level into what we call energy sublevels, okay, energy sublevels. And these now describe the various shapes of the probability space, okay? And so this is kind of like now dividing each floor, okay, into different units, okay? And interestingly enough, in the case of the atomic condo, it's not like your regular condo where as you go up, all the floors have the same floor space. In the atomic condo, it actually spreads out this way. It gets bigger and bigger as you go further and further up, okay? The amount of floor space increases. So we don't want to just have one big open area. We want to subdivide it into smaller units. And that's the whole idea behind this sublevel. You're dividing up into different, okay, subunits, okay? And in this case, okay, what we're going to do is that we're going to label the sublevels with letters, okay? And we're starting off with S, and then P, D, and then F. And then afterwards, we're going to go in order of increasing energy. So S, P, D, F, and after that, F, G, H, I, J, according to the alphabet, okay, in order. And in general, there are going to be n sublevels in each main energy level. What does that mean? Well, n is equal to 1, the first energy level, there's going to be only one sublevel. So in other words, one big lobby. When you go to the second floor, n is equal to 2, there's now going to be 2 units, okay? When you go to n is equal to 3, there's going to be 3 units. N is equal to 4, 4 units, and so on and so forth. Every time you go over a floor, the floor number tells you how many units are going to be in that floor. And the different letters basically describe the different shapes that the sublevels can be in. Imagine, again, this is a space around which electrons can be found, okay? So, for example, for the first letter S, okay, the reason why we use S is to remind us that it is a spherical shape like this. So you can imagine a nucleus in the middle, okay, and then this spherical shape around it, that's the region of space where you can have a chance of finding electrons, okay, and this is now called the S sublevel, okay, with this shape spherical. The P sublevel now describes something that looks like this. In terms of shape, it is now a pair of regions that kind of look like this, like a little dumbbell. So P for pair, easy to remember, okay? And again, imagine nucleus here, you have this, okay, region where both of these now have the probability of finding electrons in either side, okay? And then, of course, it goes up to others, okay, D and so on and so forth. And we'll see some of these shapes a little bit later on, okay? All right, to the next quantum number, okay? The next quantum number is now called the magnetic quantum number. And what this does is that this magnetic quantum number are now called the orbitals. They are the actual, okay, spaces within which we can find specific electrons. And they describe the orientation of an orbital in space, okay, of a particular sublevel in space. So in this case, what it is that we're dealing with 3 dimensions. Okay, we're dealing with 3 dimensions. And we need to kind of understand that when we get to the sphere, for example, it's pretty easy. Regardless of how I look at it in all 3 dimensions, it looks exactly the same. But when I get to the second sublevel, in this case, the P sublevel, this is no longer going to be the same. So for example, I can have it lined up this way, okay, but when I change the orientation, it is now a different orientation, different set of space, so to speak. When I do this, change orientation, another different set of space. So now I have to kind of worry about those types of possible orientations that, okay, you can take in 3 dimensions. So what does this do? Well, what it does is the following, okay? In general, okay, you will find that for each energy sublevel, there can be a number of orientations that is given by 2n minus 1, where n is the principal quantum number for the main energy level where the sublevel first appears, okay? It sounds kind of strange, but okay, it's not that bad. So for example, in the first energy level, on the first floor, n is equal to 1. Okay, we know that there's going to be one sublevel in there. And so when you have 1, okay, this is where the S sublevel first appears. 1, okay, 2n minus 1 is 2 times 1 minus 1 gives you just 1. So there's only one, okay, quantum orbital in there. This you can think of as kind of like rooms in the unit. Okay, so this is just one big unit, okay, one open area. But now when you go to the second floor, n is equal to 2, you now have the S and now P. The second one now appears. Okay, in the S again, there's only one unit, so everything's just 1. Okay, but now in the P, okay, P first appear on the second floor. So n is now 2 for P. So 2n, 2 times 2 is 4, minus 1 give you 3 possible orientations in the x, y, and z direction. In this case, it's like dividing the unit now into 3 different rooms, okay, 3 different rooms. Each room, okay, separate from the next, okay. When you go to the third level, now you have S, P, and now the D sublevel appears in that floor, okay. Now again, that's a new unit. In this case, it first appears in the n is equal to 3 level. So 2 times 3 is 6 minus 1. It gives you 5 orientations. It is now, there are 5 rooms in this particular, okay, sublevel, and so on and so forth, okay. It becomes a little bit more clear when we visualize it a little bit more. So let's kind of take a look at what some of these look like. So for example, okay, if we're kind of visualize it, we can now see that the S level looks like this. It's just basically a sphere like this, okay? And it doesn't matter how I rotate it, I will still see the same sphere. But now when I go to the second sublevel, the P sublevels now, okay, the P orbital, we now see this lobe of 2 connected together, this pair of lobes, okay? But notice in this case, it's lined up along the X direction. I can then take this and rotate it, for example, along to the Y, changing the orientation. And finally, I can rotate it and change it to the Z orientation. And that's what it might look like. Now, it's going to be hard to see because we're seeing them separately. So what I like to do is kind of go over to the demonstration area, kind of show it to you visually in 3 dimensions to see what it might look like. Okay? So let me go grab these guys and walk over to there. Okay, now let's go ahead and take a look at first the S, okay, sublevels. Remember the S sublevels are in the case of spheres like this. So in the n is equal to 1 on the first floor, you might have a sublevel that looks like this. We're going to call that 1s. 1 meaning the energy level, S the shape. It's kind of like the floor and the unit. Okay, floor 1, unit 1. Okay, and now on the second floor, you have another one that looks like this, except this time it's the second floor, okay, S level. So in this case, 2s is here. And this is kind of, imagine this to be nested one inside the other. So as it nests inside, this is on the first floor, this is now the second floor. Further away in general, okay, from the center of the nucleus. Now when I have a third floor, here's a third floor S orbital, okay, and now when I bring that in there, again, you can kind of see this nested one within the other. So S is pretty easy. They all line up like this, and you can imagine them all sitting inside concentric circles going further and further out, okay. Now in the same way, once you get to the second floor, you now have a new sublevel coming out, the P's. The P's, as we said, look like this, right? We have this. Now, in this case, this is just one of them in one orientation, in the X orientation. What if I take one now and put it in the Y orientation? So I take another one. I can now nest them together and stick them both into each other. So they now occupy the same space where the nucleus is now in the middle right here. Now I have a third one. The third orientation is now the Z orientation. Now when I put it in there, you now see all 3 of them, okay, all in there in a 3-dimensional configuration like this. Okay? So in this case, what you see is, okay, X, Y, and Z. Each of these now is, okay, a particular location where you have 90% chance of finding a particular electron in there. Okay? So that's where this looks like in terms of a 3-dimensional configuration. So if you can imagine, okay, the sequence of events starts like this. So closest to the nucleus, all you have is just a single, okay, 1s, okay, orbital. And then as you go to the second level now, you bring in, now this is now the 2s. So this is now nested inside. With the 2s, not only do you have this, but now you introduce the 2p. So this is now going to be in here, okay? And now once you are available, so this is 2s, you have taken up all the space in the second energy level. You now go to the third energy level. In the third energy level, you now introduce the 3s. And with the 3s comes now the 3p, okay? So again, this is now going to be nested inside of all this. And all the others are still nested inside. So you're going to imagine what's going on. Now, it gets even worse because now with the 3p, okay, that's not it. No, that's not all. You also now will have the 3d being introduced in the third level, okay? So things get nested pretty quickly, but the idea is you're expanding further and further out. Okay, everything is now getting complicated near the center. So to see all this put together, let's go back to the presentation. Okay, so far we saw the p orbital. Okay, so let's see what the d orbitals now look like. Okay, so in this case, we should be expecting 5 different d orbitals. So the first one looks like this. Okay, it's like a double lobe. So d for double, that's the way I tend to remember it. And so this is the first orientation. As you rotate it, you get a second orientation. Okay, rotate it again, you get a third orientation. Then fourth orientation. Now the fifth orientation is kind of interesting. It actually changes shape somewhat. Okay, so now you have a double lobe with the donut shape in the middle. Okay. Now, of course, it's kind of hard to imagine all of this, when you kind of see them separately. Sometimes it's nice to kind of put them all side by side and see them all together. So while this is a pretty crude animation, what I like to do is kind of show you something a little bit more interesting. And this is actually a website you can go to on your own as well. So let's go ahead and go to that website and see what this looks like using a better graphics. Okay, so here we are. This is a website called the Orbitron. Okay, it is a website in England. Basically, what you can do is you can actually go to this website by going to Laulima. I would have the link available for you. So if you go to resources, you'll be able to click onto the link, and you'll be able to go ahead and look at this on your own as well. Notice on the left-hand side, they actually have the different levels here. So level 1, level 2, level 3, they basically represent the main energy levels. Okay, so quantum number n is equal to 1, 2, 3, and 4, and so on and so forth. And then in each of the levels, they now show you the sub-levels. So remember, in n is equal to 1, there's only one sub-level. N is equal to 2, there's 2 sub-levels. And then go to 3 and 4, and so on and so forth. Okay? And each of those sub-levels would then have different orientations. So let's see what those look like. Now, this is actually a calculator that will allow you to calculate the shape using Schrodinger's equations. For us, we're not going to worry about it too much. So in this case, the first level now looks something like this. All you have is a spherical region like this, spherical space. And this is now near the center, so this is where the nucleus would be right there in the middle. Okay? Now, if you go further out, up to the second level, the 2s now look like this. Okay? It is now, again, a sphere, except now you can imagine this to be bigger and extending further out. And notice that little interesting internal structure there. Well, guess what that is? That's where the 1s is located. Okay? So there's that little intersection between the 1s and the 2s as they nest within each other. Okay? Now, of course, in the second level, you also introduce now the 2p. So here's the 2p right over here. So these are something that we've seen before. Okay. So for the 2p, you now have the 3 orientations. X, Y, and Z orientation. Double the lobes there. Then if we go to the third energy level now, the third energy level will again have the s. So this is now 3s. Notice now again, the 1s and the 2s are also nested within it. Now, interestingly enough, the 3p look like this. So as you would imagine, it can actually, again, intersect with the original one, the 2p from before. You now have these type of dumbbell shape that are becoming a little more complicated in the middle. And then this is the first time that the d are introduced. So these are now the d orbitals, and there are going to be 5 of them right here. So you can see the 5 different orientations that we just saw earlier. Now things get more interesting. When you get to the fourth level, you now have 4s, 4p, 4d. And again, let's just take a look at the d. This time now, again, you have the 5, but now you can see the internal structure from the previous d that are nestled in there as well. And this now introduced the brand new sublevel of f. So this is now your 4f sublevel. And in this case, there are now going to be 7 orientations. And these are now looking really funky. So there are now 8 different lobes in there, and also 3 of these donut shapes. So 4 of the 8 lobes, and then double donuts for those. And you can actually go on to the next level, to the 5th, to the 6th, to the 7th, and so on and so forth. I'll leave that up to you to kind of play around with and kind of investigate what some of these look like. But remember, these are just the shapes of the regions of space where the electrons are going to be found. So keep that in mind. So far, we haven't put any electrons in there. These are like the shells, the empty space within the atomic condo that you're just basically creating before you actually occupy them with actual occupants. So let's go back to our presentation. This is the d orbital again. What it does now, it brings us to the last energy, the last energy state of an energy described by the 4 quantum numbers. And this last quantum number is now called the spin quantum number. This will now dictate the final position, location of an electron. And in this case, it has to do with the fact that electrons can spin. And the spin can actually occur in 2 ways. It can either spin one way or the other. So there are 2 different electron spin configurations. So for example, an electron can spin in this orientation. So as you see it, it's actually spinning from left to right. In that case, if you use your left hand rule, if you follow the spinning with your left hand and the thumb points downwards, it is called a spin down configuration. We can also have the electron spinning in the opposite direction, in which case we now have a spin up orientation. So interestingly enough, when you have an electron, it can spin one of two ways. Okay, it can either spin up or spin down. Okay, dictated by this orientation that you're looking at. Okay, and so what does that mean? Well, that means that, as it turns out, that they are now going to be actually compatible within a certain location. So in this case, okay, the two electrons spinning in opposite directions can actually occupy the same orbital. In other words, okay, they can be roommates, okay, in the atomic condo. So that's kind of interesting. So when you put an electron into a particular, okay, atom, you have to specify these four things. You have to specify, first of all, okay, what floor that electron is going to be on, okay, what unit it is going to be in of that floor, what room of the unit it is going to be in, and in that room, whether it's going to have a roommate or not, okay, whether it's going to be by itself or pair it with a roommate. And so that's kind of interesting, okay? And so this really gives you the outline. So if you can imagine, again, in terms of that condominium concept, it is, I think, a little bit easier. I know it is easier for me to kind of conceptualize, okay? But the whole idea is that, okay, these four quantum number specifically dictates, okay, a particular location for a particular electron. And there is even a rule that governs this, okay? There's something called the Pauli exclusion principle that says that no two electrons in an atom can have the same four quantum numbers. So they may have the same principal quantum number, they may have the same angular quantum number, so in other words, same floor, same unit. They may even have the same, okay, magnetic quantum number, same room, but they cannot have the same spin. Okay, so if they find themselves in the same floor, same room, same unit, and same room, they must have opposite spin in order for them to be compatible in that room. And that's how you then, okay, use these rules to basically start filling in the, okay, atom with electrons as you build up, okay, atoms themselves. Okay, and we'll see this process in the next couple of units as well, the next couple of sessions. Okay, all right. So what does it look like? Well, it looks something like this now. You can imagine a condo, blank to begin with, and divide it into different floors, 1, 2, 3, 4 floors. And within each floor, you can now subdivide them into sublevels. So 1S there, okay, 2 sublevels, 2S, 2P, okay, 3 sublevels, 3S, 3P, and 3D, 4 sublevels, okay, 4S, 4P, 4D, and 4F. And you can continue to go up, okay, to however many levels you need to accommodate all of the electrons that are in there. Of course, each of these sublevels would then be subdivided into, okay, orbitals, and then you have occupancies in there. Okay, so that now, okay, kind of wraps up what we're going to be doing today. So let's go ahead and take a look at a review of what we have just done. So in our review, okay, we looked at the dual nature of light to begin with. We looked at Bohr's atom of the hydrogen, okay, which is very successful. We then looked at matter waves and the proposal of wave mechanics. We then looked at the quantum mechanical model for the atom. And so that now brings us to our next think tank question. So think about this one. Okay, some heavy metal atoms actually emit X-ray photons in their spectra instead of visible light or UV or infrared. So the question then is, would this be the result of electrons transitions between energy levels that are close to the nucleus or energy levels far away from the nucleus? Okay, explain why would you say one or the other. In other words, as the electron makes transition, is it because they are making transition near the nucleus or far away from the nucleus that they're emitting these really high energy photons in the X-ray region? Okay, so think about that. Okay, until next time, this is Roger signing off. Okay, think physics.